Okay. Good morning. I'm Milene Guiar from Toronto International. Julian Toronto and I will be your host for today. After the presentation, we will have time for questions. Feel free to send your questions using the Q&A box at the bottom of the Zoom page. Please use the option send to everybody, send to everyone, not only to the presenter. I'd like to welcome Alan Wyatt, who will present the webinar today. Alan, feel free to introduce yourself and start whenever you want.
Okay, well, good morning, good afternoon, good evening, wherever you are. Again, as Milene said, I'm Alan Wyatt. I'm a consultant, worked on water loss for many years, and I'm here to sort of throw out an idea which I wanted to introduce for discussion and evaluation by our community of water loss people. I think it has some very interesting capabilities, but needs scrutiny and trial run in different countries. So having said that, I'll begin. I do want to mention that one of my collaborators, Dave Pearson, will be presenting some of the slides. So I'll just move right in. This, okay, let me get, why isn't it going? What am I doing wrong? Okay, this is a little preamble about the spirit of this little adventure that is presented in this presentation. Think different, find a new path, try it, share it, kick the tires, evaluate it, refine it, put it out there, and see where it goes. Think out of the box. That's kind of what this is about, but also sharing and working together. Okay, the agenda is to go over some basics on real loss indicators, introduce this new, in quotes, indicator, which we call CRLI, and Dave's going to present some results of initial application in the UK. I'll present some analysis I did on Chile, the US, and then look at the technical rigor of the indicator and wrap it up from there. Okay, Stuart Trow, who I think is online, said to me one time some years ago that the best indicator of the annual volume of leakage is the annual volume of leakage. If you divide it by anything, you have changed it. And I think that still holds true today. But this indicator might come close. So what we want instead of an annual water loss is a unit real loss indicator that we can use to compare utilities across different places or a utility over the course of time. And ideally it would be simple and accurate and not influenced by variables that are out of control of the utility. We can start with gallons or liters, and to make it a unit indicator, we need to divide by something. Connections and main lengths are the most common, as is unavoidable real loss. So if we take a quick look at these indicators, we have the unit real loss volume per connection and the unit real loss volume per mains length. And they're both relatively straightforward and easy to understand. The volume per connection is more commonly used, but it tends to rise at low densities due to the math of the UARL formula, while the volume per mains, that's a typo. It tends to rise at high densities, excuse me. The point is they're both affected by density, so that the current practice is that above 20 connections the volume per connection is strongly recommended by IWA and AWWA, whereas in the lower densities, the volume per mains length. Now this creates some complications and inconvenience, and you got two indicators to cover the full spectrum. And one of my ideas in the background was trying to find an indicator that would work across the board of densities. The other one that's quite common is the infrastructure leakage index, which is built up through the UARL formula on components. And this makes it a, let's say, a very important tool in that it constructs the indicator from what's actually happening. It tells you how much reduction could be achieved based on some assumed parameters, break rates, and et cetera. It's been widely used around the world. And as I'll show you, the technical rigor in the studies that I've done show it to be quite high, but it's kind of complicated for non-technical people to understand. Now, there are a couple limitations on it in that it can only be applied down to a certain size of utility, and that's a sort of an issue in the United States in that there are very small utilities to which the recommendation is do not use ILI, and that certainly would be the case in some other countries. It is influenced by pressure in that if the pressure changes, let's say it goes down via pressure management, in some cases the ILI will go up, and that's counterintuitive and creates a disincentive for pressure management. And according to the developers of it, it's not recommended for target setting. Now, those same people have been working on a method to improve the UARL, and this is getting into very system-specific correction factors, which I'm sure they are good, but add complexity. So here's the idea with the new quote-unquote indicator, combined real loss indicator, or CRLI. Imagine a cross plot with the y-axis having gallons or liters per mains length, and the x-axis with gallons or liters per connection. And you can get a mathematical product, x times y, and that creates sort of an ugly looking formula with gallons squared and days squared. But it has both of these denominators and both of these factors that influence connection density in it. So the trick is to take the square root of that product, and then you get gallons per connection miles to the square root per day. And you can think of this as gallons per network component, you know, gallons per piece of hardware per day, or liters. It's like a blended infrastructure parameter. Like I said, we call it CRLI. The cross plot isn't really needed, but it really helps you visualize the situation of a utility in comparison to others. Now, it's a balancing act of the two denominators and the two sources of leakage. All right, now math shows that you have lines that go out from the origin up to the upper right, and those are lines of equal density, connection density. But overall, the more you head to the upper right, the larger the leakage, because both gallons per mile and gallons per connection are high. Understanding on the cross plot where the high density sites are and where the low density sites are gives you an understanding of the picture. Typically, if a utility is improving their real loss, they would move toward the origin along the density line unless they're adding many connections or you know, density is changing. But that's the general trend. Now, you can put what we call iso lines or iso curves on that XY plot and draw those lines with different values of the CRLI. And the range in the United States, or using US units, is about 100 to 1,000. That's not absolutely the case, but that's a typical range. Now, by convenience, and the trick of units, it comes out that it's a ratio of 3 to 1 for metric units. It just chance, you know, that came out that way. So the range is in the area of 300 to 3,000. I do want to point out, let's see, I don't know if you can see can you see my mouse? I don't know if Dave, maybe Dave can answer.
Yeah.
Okay, these numbers here are a density number. Okay, so they're not a value of the CRLI. So, you know, there's a low density site over here. All right, now we can also change the axes to logarithmic. And what that does is take the iso curves and make them into lines. And the density varies along the line, with the higher ones being up here and the lower density ones there. And as Dave will show, you can draw density lines on this plot. But what this does also is it sort of creates performance bands between the levels of CRLI. And that would be kind of for comparative assessment. Maybe target setting, although I think that needs a little more work. Now, I want to run through a few attributes of the indicator. First of all, it's valid for any size. It's easily developed from the water balance. And as I'll show you in a minute, the uncertainty is lower. Well, I'll just go through the slides that address these points. I think that'll be easier. All right, this is a standard IWA water balance. I imagine you can't read all the numbers, but I direct your attention down to the bottom here. This is for a large city in the southeast of the United States where they have pretty good metering. So the errors on the total real loss is pretty low. I mean, the uncertainty is pretty low. But what we find is that the CRLI has a lower uncertainty than the simple unit volume indicators. And that's probably, or is due to the square root in the CRLI indicator. And so that's an important advantage. Right away, with the same set of conditions, we're getting an indicator with more narrow uncertainty. And I do want to give a thanks to Bradley Jenks, who helped me a little bit with the law of propagation of error to make sure I had this one right. Here's a graph from Brazil where you have the lines of CRLI. Notice some of them are getting in the neighborhood of 10,000 when I had said 3,000 was sort of a typical high end. But the data comes from the national database in Brazil, and they have some data on intermittency or continuity of supply. And one of the sites which suffers low continuity is Embasa here. And if you apply the WSP correction, you see that Embasa jumps way up to a higher level in the CRLI cross plot. Whereas a utility like Sanepar that's running 24/7 pretty much stays where it is. So you can look at how intermittency impacts things. Next is the relationship with pressure. And what I did here is I looked at CRLI per unit pressure, and then I plotted it against CRLI, and I did the same thing with real loss in gallons per connection. And what you see is both of these indicators reflect pressure in the way that we would expect, and there's not a huge variation there. But I did this plot based on Georgia, and the different colors represent different pressure bands. So for example, these purple ones are for quite low pressure, 42 to 50 pounds. And you'll notice that there's some purple ones that are up in this higher area. There's one, there's another one. Now the very high pressure band is in red, and they're sort of towards the upper end, but there's one down there. So what this is saying is that pressure does influence the situation, but there are many other factors, including pipe material, age, soils, transients, but also the practices that are being undertaken. And Dave, I think you had a comment to make on this slide, if I'm not mistaken. Did you want to add anything there?
Yes, I think, obviously, I think different utilities will have different levels of practices in terms of how much leakage detection they do for proactive surveys. And the better they are at that, the lower the leakage will be, and they will move down that sort of towards the origin, as we've said. And they may have the same pressure, but then they may also then reduce pressure, and then they will also come further down towards the origin. But it is quite interesting, if you like, to be really good, to be the closest to the origin, you're going to have to do everything. You're going to have to do good leakage management and low pressure. And it's interesting to see that all these down here in this bottom corner are the low pressure ones. So that was only my point.
Yeah, good, good. Okay, thank you. Now there's a look at the influence of connection density, and this is one data set from Georgia and 155 utilities. The connection density ranges from 9 to 105 connections per mile, which is quite a broad range. And using the common gallons per connection per day, we see a rise in the curve fit, although there is quite a bit of scatter that corresponds to the UARL, thinking that it rises, all other things being equal. Now, if you take the same population with the same practices they're undertaking, same data points, and you compute the CRLI, we have a much, much flatter trend. We don't see a spike, so to speak, at low density. And this is getting down to 10 connections per mile. I mean, that's under 5 per kilometer, about 5 per kilometer. Now, this is the same plot in California. Again, there's quite a bit of scatter, but again, the density does not seem to have a significant impact on the CRLI, but obviously other factors impact performance. Whoop, I went too far. I'm sorry. Whoa, I'm going the wrong way. Okay, now we pass the mic to Dave and take it from here.
Okay. Hello, everybody. I can't say good afternoon. I can for those that are in England. But welcome to everybody else, wherever you are. So I'm just going to briefly go through a few slides just to show how this sort of indicator can, as I've used in the UK. Ofwat did use the cross plot, but then Alan Lambert looked at that and said there was no interpretation. Well, you could interpret it, but you need to actually divide each axis by pressure, and then you actually becoming very similar. You can put lines of equal ILI on it, and he produced this graph, which was in one paper, I can't remember which conference.
I'll need to change the slides for you, so tell me when you want to go to the next one, Dave.
Yeah, okay. So it can go on to the next one. So looking at recent data in the UK, there are companies in England and Wales which are privatised, and they're regulated by Ofwat, an organisation called Ofwat. The utilities up in Scotland and in Northern Ireland aren't privatised. They're what we will call quangos, quasi-national government organisations or similar structures. And each have their own regulator, but actually, because they only have one company to regulate, they actually do tend to share a lot of information and use the Ofwat models to compare performance. They have a price review process in England and Wales and Scotland, I think it is, every 5 years. In Northern Ireland, it's every 6 years. And that price review process includes setting of prices for the next price review period. And then, but they also may set targets for performance. So for example, they will set leakage targets. So there's been quite a tough price review period for England and Wales, which has come into operation this April. And companies have signed up to leakage reductions of 15% and in some cases 25%. So the graph shows you a plot which Ofwat is used a lot, particularly in the 1990s, which is what we've shown quite a bit this afternoon. So you've got the x-axis, litres per property per day, and the vertical axis, metre cube per kilometre per day. And you can see the splatter that you get for the different companies in the UK. Ofwat didn't offer any form of interpretation, but obviously we know that as you reduce leakage, you'll move towards the origin. So if you go on to the next slide, that's the same plot, but now I've added, first of all, the lines of high density. So you'll see that the company with the highest density is Thames Water with about 125 properties per kilometre. And the utility with the lowest density is Northern Ireland Water with a density of 32 properties per kilometre. And then I've also put on the isoclines, iso curves of CRLI, ranging from 500 black to up to 2,000 here in red. I've also added what can be classed as the isocline for the Frontier company. Alan will mention Frontier a bit later on in the presentation, but basically the best performing company here is Anglian Water with a CRLI of 655, and the dashed red line here would be the Frontier performance. If any other company, for instance, if Northern Ireland Water came from there down to here, it would be performing the same as Anglian Water. If we look the other way, then leakage in Thames is about 3 times the Frontier company, so it's just short of 2,000 compared to 650. Okay, now that's the normal axes. In this case, this is the same plot, but I've now taken both axes have been converted into logs. And so you get this effect that Alan has mentioned. the curly lines become straight lines, and the density lines, which you saw emanating from the origin, become parallel lines running across those curly lines. So just the same graph. It does have the advantage that in some respects it can be a bit easier to interpret which companies are similar performance to other companies. And also it does open up this, because as leakage is reduced, everybody's basically moving towards the origin. You do tend to get a cluster, you can get a cluster in that bottom left-hand corner, and that can make it difficult to decide who's who. The advantage of the log-log plot is that it opens up that bottom left-hand corner.
I can just show here, you've got them all mashed in together on top of each other.
Yeah. But some people are not as comfortable with log plots as linear plots. Okay, so that was working on, do you want to move on to the next slide? That was working on different utilities of different operating companies. But this is an example of if you took different zones within the same operating company. If you've got a large company, it becomes quite difficult to manage a large company, and you might have a wide range of connection density between zones. In this case, the connection density is from 15 properties per kilometre to 160 properties per kilometre, so that's wider than the previous slide. And it can be quite difficult, and I can assure you on this, based on personal experience, having discussions with local managers responsible for leakage in this area compared to the local managers responsible for leakage in this area. And so having some indicator which you can care as a single number that you can compare performance between different zones with different connection density can help. So if you move on to the next slide.
Sorry, what am I getting here? Uh-oh, I know what's wrong, sorry. Okay. Yeah, okay, there we go. Sorry, Dave.
That's it. Yeah, if the ISO lines are added onto the curve, you can see now that this guy here, this zone manager looking after this zone, on the face it has the worst litres per property per day. But in fact, when you look at it as a curly, is actually in the middle of the pack. Is actually quite reasonable performance. And you can work out which is the frontier zone, which is the best performing zone, and it would be feasible to set targets for the next year, say, based on equal, say, percentage reduction towards the frontier zone. That is the type of process I used when I was inside the business. Fortunately, with a bit of luck, your frontier zone will also improve, so then you all have to improve a bit more the following year. Ofwat was very good at that. Anyway, I think that's the end of my slides.
Good. Well, thank you. I think that last point you made about how this one would be judged worst using the liters per property, but its relative position changes using the curly, and that's a informative comparison. Now, before I go to the next slide, I just want to mention that there has been use of this indicator in Canada by Hydrotech, if I have that name correct, Fabian Papa and Bradley Jenks, and you can see the YouTube of that webinar, or they did a webinar on May 25. So you can look at all their good work on DMAs and also use of this indicator. All right, moving ahead now to South America, in Chile, where you have a very good data system, which allows a lot of analysis to be done. For example, they have mains length by pipe material, mains breaks by pipe material and diameter, replacement rates, age of water meter. I mean, you know, resolution rate on complaints, you know, just an amazing database. And so I applied CRLI here, and I just want to point out the limits a little bit. You've got one small utility way in the far south that's very low CRLI, going way up to this one here, which over 4,000. So the range is very broad. Note that the density seems to be in a fairly narrow range. There's nobody way over here or way up there. Now, what I did was to take their position on the CRLI plot and adjust the size of the data points based on several factors. So for instance, this one up here that we noted was way high in CRLI also has a relatively large area plot, which is related to the total real loss volume. This goes back to what Stuart was talking about the, or in the quote from Stuart about the, you know, total loss is the total loss. Well, those ones that are performing really well are very small in terms of their leakage volume, whereas Aguas Andinas is kind of the elephant in the room. They're moderate on CRLI, but the volume is quite high. Now these two plots are the same thing, except the one in green is where the diameter of the circle is related to the real loss volume. And what that ends up doing is making some of these small ones almost invisible. I thought that this approach of not only what is their unit performance, but at what scale are they at? And then I did another one where I looked at the area relating to the cost of water. And you see the variation in the area is not very big. Aguas Andinas, in fact, has a very low price of water. So their higher leakage may in fact be a rather close to optimal. But the high unit loss as measured by CRLI is combined here with a reasonably big size of cost of water. So they're really kind of noticeable as a point of concern from a comparative standpoint, or let's say a regulatory standpoint, because they're taking reasonably expensive water and sending it into the ground. Note that the ones that are very small have fairly high prices as well. And you could try lots of different parameters this way to look at the impact of different variables and identify strong and weak performers. Okay, now I'm going to jump to the US. And this is Georgia, state of Georgia, not the country. And the familiar lines of curly, you have a fairly wide spread of densities here. The range is pretty good, below 50 all the way up to around 1500. Sorry, I don't have the label on here, but now what I've done here is to start to look at cohorts, that is certain parts of the state of Georgia, and they have what they call water planning districts there. And this is the Metro North Georgia Planning District, which includes Atlanta and utilities in that region of the state. And those are the bigger blue circles here. And you can see it ranges quite a bit. Atlanta is way up there and known to be a problem. But there's no particularly noticeable difference between that planning district and the others, perhaps with some exception of these points way up here. A little bit narrower span, I guess you could say. There's some ones that are better and ones that are worse. But if you're in Metro North Georgia and you're trying to regulate things or examine performance, understanding that is important. Now, what I did here is I compared Metro North Georgia to the statewide lines and of curly, and in fact computed the percentile of Metro North Georgia against the overall state. And this again shows a tighter span of performance, not by a large bit, but somewhat. It shows a lower median, 230 versus 304. But administrators or utilities in this region would have roughly similar conditions in terms of water resources and economic levels, densities, whatever. So you might want to use the percentiles to assess performance for that region, or you may just want to use the whole state. But this indicator can allow you to zero in on certain zones and look at comparisons within those zones. Somewhat like Dave was talking about. Okay, I think this is out of order. I'm sorry. No, I guess I'm going into California now. That was quick. Okay, California, I have 272 utilities in a filtered database. This is a repeat of the slide that I showed before on density relationships. And this is the cross plot for California. They're much more clumped together in terms of density, not much variation this way. You can see some household names like San Francisco, LA, East Bay Municipal, Folsom Prison is way up there. Now, I again looked at percentiles, and what I found was these bands, so to speak, and quartiles are commonly used in looking at performance, maybe not for target setting, but looking at performance. And what I found is that there's kind of a tail of bad performers. In other words, stretching way out. This is not a normal distribution of leakage. So 20% are below the 25th percentile down here, which might be considered pretty good performers. But no, 20 is in this range of lower than 25th percentile, but 25% are out here in this long tail. So in looking at this, some people in California said, okay, let's focus in on these people and not worry about those places too much. And that's not illogical, but would only be a sort of a first step. You'd want to dig into the situation in these places some more to really understand and look at what needs to be done. All right. The next part here is about assessing the technical rigor of the CRLI indicator. And I've used the frontier analysis approach, which was used in some previous work that I spoke about in a previous webinar in May. And a paper on it was just recently published in the IWA H2 Open Journal. You can download it. It's not copyrighted or anything. On the left side here, you have the 4 major steps of the process, in that you develop a multivariate regression for the water losses based on mains, connections, pressure, water cost, et cetera, and then plot those modeled values against what in fact utilities do. So this utility here is performing at a level much higher, it has a much higher observed loss than what it could do according to what the model says. And this utility down here is right at the frontier, so to speak, of performance, in that their observed level is better than the modeled. They're below this average line. Now, the next step is to develop an indicator or a score based on the length of the line from the utility to the frontier. And I call that a frontier score. And if an indicator is a good indicator and my regression model is good, then this frontier score will be a good indicator of the leakage performance. And then I can take other indicators like ILI or gallons per connection and compare them to the frontier score to see which ones correspond best to the frontier score. So that's what's done and explained in the papers. Here's some results. The differences are not huge, but the CRLI had a tight relationship with the frontier score, R squared of 0.878. Here, with gallons per connection, there's more scatter, and that may be related to density or any variety of other factors, but the R square of that relationship is not quite as strong. Now, here I've compiled Georgia with a number of different potential indicators, from gallons per mile, gallons per connection, the ILI times the PMI, which is a pressure management index, which is essentially a ratio of what the pressure is to a modest or low reference pressure. And it has generally been found to be quite rigorous in the paper that I did. But CRLI is at that same level or a hair above. So overall, we can say the CRLI comes out well in the technical rigor in Georgia. Now, here's the same thing for California. And again, the CRLI and the ILI times PMI are at the top of the list, almost, except gallons per mile is the top indicator. And Julian can tell us why that is. He told me a story that explained this. But nonetheless, CRLI has a high technical rigor in this and other cases I've looked at. So just to wrap up, I think that we can say that it's a useful measure. It's not excessively influenced or unexpectedly influenced by important parameters. It's good for comparison over time and by location. You can use cohorts to compare peers or utilities in the same region or conditions. Easy to calculate. Pressure is not needed to compute it. Doesn't mean that pressure doesn't influence it, but a lot of utility-based databases do not provide pressure, such as the one in Chile and the one that I think very highly of in Portugal. The AirSAR data does not provide pressure because of concerns of accuracy of the number. As I said, works in emit and supply situations, scores high on rigor. And this one I think is quite important. Lower uncertainty in the water balance than other real loss indicators. Seem to have duplicated one bullet there. Anyway, I think some additional testing and evaluation, you know, kicking the tires, so to speak, would be good. I'd like to do Portugal, and I threw out some other countries, Brazil being one, South Africa, Malaysia, South Korea. You know, if anybody has other ideas, I'd be interested. I think that for the early work or of assessment, countries or locations with good data is the most important factor in terms of testing purpose. Okay, I think that's about it. I do want to acknowledge the contribution of a number of people who reacted to this idea, contributed greatly to it, like Dave and Stuart, and Bradley Jenks, who helped on a few things. You know, people have given me feedback, and I owe a lot of thanks to all of them. And I think it's a representation of the teamwork that's been a part of this effort, which I greatly enjoy. And I hope it will continue in that manner. And if things come up that make this less interesting, well, fine. We will have agreed and come to that decision together. So at that point, I'll stop, but I do have my email there if you'd like to be in touch with me for any more discussions. So
thank you, Alan.
I am right about on 45 minutes. Let's see, do I do this? There we go, okay.
Alan, no, you can leave the presentation, or
all right.
Stop sharing every.
Well, I want to look at my other screen for a minute. Sorry. Okay. I mean, there's a chat thing with some questions that I, you know, if I wanted to see, I mean, I wanted to see those questions, but I guess you'll.
I'm interrupting here. Okay, that's okay right now. We've got a question here from Michael Wilmot.
Hold on.
Would you like to read it?
Milene.
Hi.
There's some written comments from Stuart Trow that aren't in your chat line.
He's answering this question that I'm telling you. Michael is saying, thank you for this presentation. Looking at the UK, some of those companies with highest CRLI have large cities, while many near the bottom are more rural. Have you any thoughts on this? Will rural areas find it easier to have a low CRLI? And then Stuart answered him, yes, this is a good point, and one we've known about for some time when doing comparisons using various KPI measures. A colleague of mine has often said that leakage is more of an urban problem than a rural one. I wonder how much of that is due to the uncertainty of customer side leakage. So would you like to say something about this?
Well, I would, and I expect Dave might. I could point to the example of some small utilities in Tennessee where it's a small utility and all of the water department knows where all the lines are, and their uncle lives over there, and they know the place. They know where breaks happen often, even though they're doing night flows every day. But, you know, they know their system very well. And it's hard to know all of London very well. And that's kind of a qualitative factor, but I think that's true. Not to deny that there might be a consumption effect or customer side leakage, you know, but something about a smaller zone that you can understand helps in handling leakage. And I'll pass it to Dave because I think he may have a comment on this.
Yeah, definitely. There's a very, very strong correlation on that UK plot. And not so much with connection density, but certainly size of companies. So the three or four highest performing CRLIs, I probably should put it that way, are the larger companies, because management within a large company, as Alan says, is far, far more difficult. You've got communication problems sat on top of all the other problems of leakage. I think to come back to Stuart's point, yes, I think possibly the lower connection density rural areas might perform better. I do know they tend to say, because their networks are so much more stringy, as I tend to call them, I think partly the leaks might be a bit easier to find because you can cut and cap and things like that easier than a reticulation, a complex reticulation. But also, quite often, because they are more stringy like that, they are more prone, actual supply difficulties are more prone to leakage. So if a burst breaks out, quite often you end up with supply problems and you have to get onto it fast, otherwise the people are without water. Whereas when you're in the middle of a reticulation, then the network tends to feed itself the other way around, just like a ring main. So there is that tendency for more rural networks potentially to perform better because of that reason. Okay.
What am I doing? I don't know what I'm doing. All right.
Okay. A couple of people were asking for the presentation, and Julian told them to ask you by email, because now they have your email here. And this presentation is recorded and will be available on YouTube, so everybody can see it again.
Yeah, I have it in the, well, a PDF is probably the easiest way to email it, but
we've got another question here. Is it better to measure a whole utilities CRLI or per DMA measurement?
Well, I'll let you answer that, Dave, since you immediately responded. I mean, I think both are important, but you answer, please.
Well, you're then touching a very touchy, sensitive area for me there. I have my own personal views on that. I tend to think that it's more for zones, say 5,000 properties or more, simply because I tend to think that with DMAs, if you're not doing normal active leakage control process, then the leakage level on the DMA will rise from its exit level to some level intervention over a period of 6 months, 9 months, 12 months, maybe 1 or 2 years, before it is deemed necessary, appropriate to go in and do another active leakage control survey. And therefore, its CRLI in that period might increase by a factor of 2, possibly 3. So I don't really see how, yes, you could argue, well, okay, we'll take the average for a year for the DMA, but certainly I wouldn't use it as I coined the phrase that's been used for ILI at DMA level, a snapshot curly. I wouldn't particularly promote that concept. Is that okay for the person who asked the question?
I think breaking the system down, some places like in the US don't have DMAs, but they have pressure zones. I mean, I think that the more you can zoom in, the more you can find out where your problems are, this zone versus that zone. A big company like Los Angeles, you know, I would certainly want to break it apart. Although you have so many different sources, and you know.
No, I entirely agree with that. Yeah.
Yeah. Yeah. Okay.
Yeah, I think we don't have any more questions. They asked it for your email, and I write it down here in the Q&A box.
I've been scanning the points that Stuart Troll made before the session, and yeah, the one interesting point it does make is that in a way, it's a bit less difficult to conceptualize curly compared to, say, ILI, because basically with ILI, you know its relative performance to what you should be able to do on that zone of the same network parameters. So you've got this straightforward ratio of 5, 3, 90, 100. So you know what you should be able to be aiming for. With curly, strictly you haven't. It's more relative. So it's not as easy to get an absolute understanding of where you could possibly be with curly. Well, you just don't have that measure with curly. So there is that interesting difference between curly and ILI.
Well, I would agree with you, but I would also point out that ILI is often used as a, oh, I've got to get down to 1, you know, target kind of approach, when that may not be the most economical approach. In fact, AWWA says if you're under X, Y, and Z conditions, you should try to be ILI between 3 and 5, you know. Well, that's not bad, but I think ILI becomes a, oh, let's set a target used on it, when that may not be economical. Now, curly doesn't necessarily give you the economics. Well, it doesn't at all. It just tells you a volume. But I think that's a danger of misinterpretation with ILI.
I have to interrupt you right now and say thank you, Alan. Thank you, Dave. It was a wonderful presentation, great presentation. If you want to say goodbye, everybody, we have 1 whole minute left for you to say bye to everybody.
Well, I really would say that I view this as a work in progress, and I welcome feedback of any type, and I hope to continue using it in a variety of places to sort of see how it goes. And if this gets picked up by more people, then that's a sign of its usefulness, and if not, then fine, you know. But anyway, thank you for listening, and again, I look forward to any feedback you may have. Thank you.
Thank you, Alan. Thank you, Dave. Bye, everybody.
Okay, thanks everybody.
Bye-bye.
Cheers.
Bye.
Bye-bye.